Hello friend, welcome to my Kadam Academy YouTube channel. We are studying the various videos on the mechanical vibration, single degree of freedom. Already we have studied the undamped, damped vibration. Now we are going to study the force vibration. Under this force vibration already we have studied the application of force vibration and the various equation of the force vibration. Equation of motion for the force vibration. Already friend we have studied what is the magnification factor, and we have derived the formula for the magnification factor. In this lecture we are going to study this frequency response curve. What is the frequency response curve and how it is drawn, and what will happen, the relationship between this frequency response curve, that is the drawn with respect to the magnification factor and the frequency ratio, as this formula shows. Magnification factor, formula for the magnification factor is 1 upon denominator the square root of the square bracket 1 minus the curve bracket omega by omega n curve bracket close its square, the square bracket square, plus this square bracket again 2 zeta, this bracket omega by omega n bracket close the square bracket square. These two terms are there under root of this one, that is the total is, you can find out by using this one, the magnification factor. Here this omega is the frequency by this force due to the force vibration, or we can say harmonic force. Harmonic force, that is the F4 sine of omega t. That is the harmonic force due to this we are studying here. And in this case what will happen, that is the frequency omega, and omega n is the natural frequency. When the ratio of this omega by omega n, that is represented by small r, that is called as frequency ratio. If you put these values of omega by omega n here in small r, so formula becomes now here, see this formula, f is equal to 1 upon square root of this inside bracket 1 minus r square bracket close its square plus 2 zeta r bracket close square. See, this is the omega n by omega by omega by omega n is replaced by this r. So this is the magnification factor, already we have studied. Now we study this, what is this frequency response curve. The frequency response curve is frequency response curve. This response curve is drawn here with the magnification factor on this side, on the here y-axis with the magnification factor, and this factor it is represented, I will show you right here, f, okay, magnification factor, and frequency ratio r, here is r. We show by this green color, this f, and this one is the r, frequency ratio. On x-axis drawn, and this block with the 3/4 draw it, and see these curve will start at one point, at 1. This graph is dimensionless plots. See here, what is the MF? MF is x by x st. This is the amplitude when there is a static deflection, and this is the amplitude at the harmonic force, and this is the ratio omega by omega n. This is also dimensionless. This graph is dimensionless, and we are studying this graph, that is the magnification factor versus this frequency ratio graph. This dimensionless plot of magnification factor versus frequency ratio for different damping factor as shown in this figure. Carefully you watch it. Here is the this curve having important characteristics. This curve, what is the purpose to study this frequency curve? Its purpose, it will help us to design a system, for our choice based on the limits of the vibration response or the amplitude of the vibration. Means we have to design any system, it is helpful, and based on our choice base. What is our choice? So we can decide according to this graph. By using this graph we can decide and we can finalize it and design it. Okay, friend, what is happening here? This graph is now, first point we clear, design a system of our choice based on the limits, the vibration response or the amplitude of the vibration. We can select our interest of frequency range that in which my system is subjected to some force. So we have some frequency range, and in that frequency range what response we are expecting. We can select the damping value so that our system response is staying in our choice. Means what? Here choice we have to decide. But what is the actual range? Means here what will happen? The frequency range. In between what frequency range we have to decide, that we can here decide. If we encouraging the damping, the response of the system is decreasing. Increasing the damping, what will happen? Means what? The amplitude x. The amplitude x is steady state amplitude, and x by x st is decreasing. If you increase the value of this zeta, if zeta is increased, see here, value of zeta is increased, what will happen? Damping controls vibration response. So is decreasing, increase the value of damping zeta. X is decreasing, this value of x is decreasing, so zeta is increasing here. This x is decreasing, the zeta will increase. See here, when we are near the r is equal to 1, here in this case, this is the r is equal to 1. When we are near the r is equal to 1, that means omega by omega n, here in this case omega by omega n is 1, for forcing the frequency is equal to natural frequency of the system. When response is very high, although we increase the damping, the response is decreasing, but in comparison to other reasons, for example r is less than 1, so much greater than 1, response is quite high. Suppose this r, okay, the r, when r is less than 1, suddenly response is high, and if small increase in r, the response is high. That is the r is equal to, here zeta is equal to 0. Omega by, here in this case omega by omega n is 0. In this case the x is nothing but the xst. When the omega by omega n is equal to 0, in this case the x is equal to xst. Means what? So definition of the zero frequency deflection. This is the zero frequency deflection. Okay. When the r is equal to 0, means we have force Fo. This Fo is constant and acting at, so the response is equal to, this response means the displacement is equal to xst. In this, due to this force xst, static deflection will be there, and thus the x by x xt become equal to 1. In that case, so all the curves, means what? At static condition, see, observe very carefully, all the curves are started here. All the curves are started at point 1. From this point, this curve will start, this point, when this curve is drawn, x-axis r, y-axis mf, and with respect to zeta, the values of curves are different, values are there. And zeta we know c by cc, zeta we can find out value of zeta is c by cc. Damping factor, damping ratio, you can say the damping ratio, you can find out. This all the curves are started here at point 1, okay, because the x by xt is equal to 1. In this case x by st is equal to 1. So all the curves are selecting at a x by xt 1. We can see there are some peaks. See here some peaks are there, or one more peak here, 0.25, 0.5 and this 0.7 is there, and here is center line. Okay, where is the zeta? Okay, so what will happen? These peaks are there for this for 0.25 or 0.5 or 0.75, like this. These peaks are there. At this meaning of this peaks is what? So we can see that the response is not taking place maximum at r is equal to 1. Means the resonance, the maximum is not taking place, but maximum is taking place little earlier than the resonance point. Where is the resonance point? Here. When r is equal to 1, resonance will be there. Maximum point will be here. Okay. Or maximum point may be here, maximum point may be here. According to system, you can observe that when we are decreasing the damping, we are more going close to the peak or more moving towards the resonance condition when r is equal to 1. When r is equal to 1. If we have the damping so such that the zeta is equal to 0. Zeta is equal to 0. So no damping is there. See, this is the zeta is 0, no damping is there. So response is infinitely large. Response is, we want to know what is the peak frequency. Then what will the peak frequency? How we can find out the value of peak frequency? We can find out the peak frequency by using the MF equation. The MF equation is, already we know that is the equation. We have x by xt is equal to 1 upon, inside the bracket, 1 minus r square, bracket close, plus twice zeta r square, bracket square. Okay, this is the value of MF. Just differentiating this above equation, this MF is going to differentiate. What will happen then? D by MF by dr, which is equal to 0. So this equation we are differentiating here. In this case, what will happen? See, differentiating d by this equation, the square root 1 upon square root. I will write here like this: 1 minus r square, bracket square, plus twice zeta r square is raised to minus 1 by 2. This is taken on the top side. So what will happen? Minus 1 by 2, which is equal to 0. D by dr, differentiation of this equation we are differentiating here, written like this. After differentiation, what is the next step? Here I will write the differentiation of this equation. If suppose I will consider this total equation as a r, and write here minus of r raised to minus 3 by 2, and inside the bracket 2 into, for this term now, 2 into 1 minus r square minus 2r, bracket, this minus 2r, okay, plus 4 zeta square into 2r, which is equal to 0. This is the differentiation. Suppose this term is taken on this side, it will become 0. Only remaining this term. We will take this term. What is this term? This term is remaining. This will, when we solve it, this is the 2 into 2, 4. Okay, this 4r and this 4r. This 4r we are taken outside. 4r minus this minus sign with this bracket is remaining 1 minus r square Okay, plus here 2 into zeta square. 2 into zeta square is remaining. This is equal to 0. So what will happen here again? This 4r becomes again 0. Remaining is this minus 1 plus r square minus twice. Here is the plus, not minus, zeta square is equal to 0. If I write equation here as E. Okay. So what is the next step? Here, see, observe carefully. This r square becomes 1 minus twice zeta square. Or we can write r becomes under root of 1 minus twice zeta square. Correct? So, friend, what is r? R is the frequency ratio. And in this case, when the maximum amplitude in this graph, friend, here in this graph, when there is a maximum amplitude, we have to find out, and for this amplitude ratio we are considering maximum by differentiating. To find out the maximum amplitude, differentiating this equation just up to this step, we are solve this omega p. It is written by omega p by omega n, which is equal to under root of 1 minus twice zeta square. Friend, what is the next step then? Here, this omega p is nothing but the peak amplitude. This peak amplitude we have to find out. Okay, this wp is nothing but the omega n into 1 minus twice zeta square. Once we know the value of this omega n and this zeta, we can find out the peak amplitude or maximum amplitude. And this maximum occurs at when r is equal to 1 minus twice zeta square. Means what? This occur maximum frequency, this which is greater than 0. Okay, to occur this term become 0, greater than 0. If we have to occur this maximum r, value of r, if we want maximum, how it is possible? This r is possible by maximum when this under root of this term is become greater than 0, means 1 minus twice zeta square is greater than 0. That means what? Take case of this positive quantity only. Positive quantity we have taken. In this case, what will happen? This 1 is greater than twice of zeta square, means half greater than zeta square. So friend, zeta is less than square root of 1 by 2, or zeta is less than, always less than 0.707. This value is very important. See, zeta is less than 0.707. At this condition, the peak value will be there. We'll show you in graph. You can see inside the graph here, the zeta is this value. Okay, this value is 0.707. Above this value, always there is a high peak amplitude. Above this value, there is a high or peak amplitude is there. That means the above this zeta is, means the zeta is less than the 0.1.7. The value of zeta here 0.5 less than the 0.707, 0.25 like this up to 0. The value becomes we have the writing for the peak, zeta is less than 707. For peak, zeta is less than 0.707. This is the important concept we are obtaining here. So friend, what will happen if we, for this peak value, what is the value of MF then? MF we want to calculate the value of MF. So what is the value of MF then? I will write here the formula for the MF. Okay. This MF becomes, how to get the value of magnification factor? Magnification factor, we can utilize this equation A. See, this is the equation A. From this we can find out the value of zeta. Of the value of zeta we can find out Cn. This value from this equation, that is the 1 minus r square plus 2 zeta is equal to 0. From this equation A, we can write this equation, we can write here like this also. See here, this 1 minus r square minus 1, this is equal to twice zeta. Like this also we can write, correct? So what is the formula for MF? MF is equal, already we have that formula for in terms of the R here. See here, 1 by r square 2 zeta r square. This bracket, we are putting this 1 by r square here, 1 by r square, 1 minus r square. This 1 minus r square is twice zeta, minus of twice zeta. We are putting here the value 1 minus r square, r square minus 1 twice zeta. Okay. So friend, what will happen here? This 2 zeta here written here for the MF is equal to 1 upon twice zeta square bracket square plus twice zeta square 1 minus twice zeta square. In terms of this zeta, we are just converted. So final equation for this one, after solving this, we get 1 upon twice zeta inside square root of 1 minus zeta square. This is the equation when there is a peak amplitude. We can utilize this equation for the peak amplitude. Okay. This MF is at when this ratio, this WP, okay, at the WP means the maximum peak amplitude. This MF is, value of MF is this one. And there is a normal case, already we have studied this equation for the, in general case, when there is a, other than this peak amplitude, we can utilize this formula, okay. So this is the only function of damping. If we are decreasing the damping, here these peaks we can find out. So we see that if we decreasing the damping, we are tending to the, in this graph, I will clear you, we are decreasing the damping, we are tending towards the maximum value, peak value. So we are going towards the line, center maximum line, means this value is decreasing less than the 0.7 or so, it is decreasing. So we can understand effect of damping if we are near the resonance condition. This is the resonance condition, and we don't have damping amplitude. We don't have the damping amplitude is 0. So that why we have to amplitude is reducing. So in this case R is 1. Suppose this R is 1. What will happen? This omega is equal to omega n. The vibration is we can induce some damping. So what is required here? In this case, we have to induce the damping, that will reduce the vibration. That is our purpose. Magnification factor is maximum when omega n is 1. This condition is called resonance. When omega by omega n becomes 1. In this case, the resonance is more. And damping factor zeta decreases, the maximum value of magnification factor increases. Here see, on this y-axis magnification factor increases if we decrease the zeta. No damping means at zeta 0, at that time omega is equal to omega n, means this case here. In this case, what will happen? The magnification factor is unity for all values of damping factors. All values of damping factors. So damping factor at very high frequency of the excitation, the magnification factor tends to 0. Very high frequency, it tends to 0, and at R the zeta is less than 707. This is the magnification factor is more, and the peak amplitude will get it. Okay, and if zeta is greater than 707.707, then MF is below unity. This value of MF is unity. See here, 0.7123 up to maximum value. See, magnification factor less than the 1. Magnification factor less than 1. This is the actual study. You must clear from this graph. Now we go for the phase difference diagram. In this graph, phase difference diagram, plot of this phase difference means the phase angle. Okay, see here the phase angle from 0 to 180. 0, 45, 90, 135, 180. This 180 is at the end, this 180 is there, and here is the 0, this 45, okay, this is 90, this 135, and this value of ratio omega by omega n, frequency ratio from 0 to 3. This curve will go through this point. Okay, so what are the observations from this graph? Already we have studied the phi is equal to, okay, tan inverse of 2 into zeta omega by omega n and upon 1 minus omega by omega n. Okay, it's square. So this is the formula for this our phi, phase angle. The phase angle varies from 0 to 0 at low frequency, and ratio of to 180 is a high frequency. The frequency is high. Friend, what will happen is when omega is equal to omega n, omega is equal to omega n, means this r is equal to 1 here. In this case, what is the actual you have observed here? In this case, the phase angle is 90. Phase angle is 90. In that case, the effect of the phase angle, does not have any effect of the phase angle, or damping does not have the effect of the phase angle in this case. Okay, the resonance frequency at omega is equal to omega 1, the phase angle is 90, and damping does not have any effect on the phase angle. So at r is equal to 0, the phase angle becomes 0. At r is equal to 1, this phase angle becomes 90 degree, and in this case omega is equal to omega n or greater than or equal to 1. At r is when r is greater than 1, what will happen? The phi be also greater than 90. In this case, when the r is greater than 1, phi is also increasing. See, phi means this, why it is given the value above 90, it will curve shown on the curve. Okay, this phase angle varies from 0 at low frequency, and 180 at high frequency. Okay, this is the phase diagram related to phase diagram. Okay, these are the observations for the phase diagram, and the previous was the frequency response curve. So friends, if you have any suggestions or any queries, please subscribe my channel and write on the comments on the channel Kadam Academy. Thank you very much.